Let's now do some variety of cases. Okay, z is equal to delta lambda over lambda. This is the general equation for z, and when beta is small, we can say z is equal to v over c, which is beta. But this is only true for small values of beta. So if most non-relativistic objects are going to have z is equal to v over c, so the ratio of b to c is going to be very small. So realistically, z is going to be a very, very small number, 0.0001, 0.0008, something very small number. What happens as z starts approaching 1? Redshift of 1. What does that mean? Well, that means z is equal to delta lambda over lambda. The shift amount is equal to the original wavelength, right? So, for example, if the wavelength of the Balmer line is 656, imagine the object is moving away from us at such a rate that it's going to look to us as it's double this amount, right? Double 656 is what? 1312. The wavelength will grow by double. So it's going to appear as if what? Delta lambda is going to be 656 divided by 656. Z is going to equal 1. How fast is this object going now if z is equal to 1? Well, you can put it into here. For example, let's put it into here if z is equal to 1. Gamma plus square root of gamma squared minus 1 minus 1, right? So you could put your z either into here, or either into here, or either into here. Now, if I put it into here, I have two unknowns. So this is not as friendly to solve them, right? Because the expression has two unknowns. This one is a little bit more complex looking. This one has one unknown, the least complex looking, right? So now if I want to solve for gamma, I put 2 is equal to gamma plus square root gamma squared minus 1. Now I could put it into solver, right? My gamma is going to equal 1.25. Okay? So now the relativistic factor, remember for objects that are going at very slow speeds, the relativistic factor gamma is 1. So that means the relativistic factor is 1.25 now. How fast is the object going? Well, now set this equal to square root of 1 minus beta squared. And so for beta. Or the other way you could do it is put that gamma equation into here. We know z is equal to 1. Gamma is 1.25 plus 1.25 beta minus 1. It's probably easier than doing this. So now you get 2 minus 1.25 equal 1.25 beta, right? So that's going to be 2 minus this. So that's going to be 0.75, right? The difference here. Divided by 1.25. Divided by 1.25. 0.6. Okay? Okay, that means if the redshift factor z is equal to 1, that object is already going near relativistic speeds, 60% of the speed of light. That's amazing, right? That's very, very, very fast. Now, the other thing we know of now is the object is going to be very far away from us, right? Go back to the Hubble law. Now, plot this on the Hubble equation. Find out if this object is going 60% of the speed of light. How far away is it from us? Well, it's probably be millions and millions of light years away. So the farther you're looking into the universe, the faster the objects are moving, right? How about z is equal to 2? You can do similar calculation. How about z is equal to 3? Z equal to 4, okay? Now, in reality, we have discovered objects with z's as big as 8, right? So let's do this calculation. If z is equal to 8, what's going to happen? Then you're going to have, this is going to be equal to 9. Right? You're going to have 9. So what's the solution going to be? Let's go back to my equation. And now I'm going to have, instead of 2, I'm going to put 9 into there. Press solve. Y is going to be, my gamma is going to be 4.555 repeating 5s, right? It's going to be huge gamma, right? And now, if I want to solve the corresponding beta, then you put it into here. Z is equal to 8, 4.55 repeating 5 plus 4.55 repeating 5 beta minus 1. So you're going to have the negative 1 is going to go over there. It's going to be 9 minus 4.55 repeating 5 divided by 4.55 repeating 5 beta. So 9 minus 4.55555555 divided by 4.55555555. Beta is going to be 0.9756. So objects that have a z redshift factor of 8 are going 97% of the speed of light. These objects are so far away that they're the very first objects that formed after the recombination stage of the universe, where galaxies began forming. So we cannot look past the recombination stage because the universe was opaque then. After the recombination, the universe became transparent, galaxies began forming, and then soon afterwards stars began forming. So objects with redshift of 8 were about the first objects that formed after the recombination stage, is the first objects that we can actually see after the Big Bang occurred. So this is a very interesting topic, how redshift combined with the Doppler factor, and then we can combine that with the Hubble law, and then we can discover how far away these objects are, so we can actually begin to understand the very nature of the universe. Thank you very much.